A telescope stared into a patch of sky smaller than a grain of sand held at arm's length. It stared for over 18 hours, and it found a galaxy glowing from 13.5 billion years ago, from a time when the universe was supposed to be completely dark. No light, no stars, nothing. We are going to go back there, back to the darkness before stars existed, back to the first galaxy that punched a hole through the universe's fog, back to an object so old its light was already ancient before the Earth even formed. If you enjoy the journey, subscribe and leave a like. It really helps. Prepare yourselves. We begin. The universe was once completely dark. No stars, no galaxies, no light of any kind. Just cold, invisible gas stretching in every direction for hundreds of millions of years. And here is the part that should stop you cold. This darkness was not a beginning. It came after something. Before the darkness, the universe was a blazing fireball. Every direction, pure energy, pure heat. The kind of heat where matter itself cannot hold together. Protons and electrons were flying free, crashing into photons constantly, like a room so full of bouncing balls that nothing can move in a straight line. Light existed, but it was trapped. It could not travel anywhere. The universe glowed, but it was blind to itself. Then something changed. About 380,000 years after the Big Bang, the universe cooled enough for a single, quiet event to happen. Protons and electrons slowed down. They stopped bouncing apart. They locked together into neutral hydrogen atoms for the first time. Scientists call this recombination. And the moment it happened, light was free. Photons that had been trapped for hundreds of thousands of years suddenly had a clear path. They shot outward in every direction. That ancient flash of light still exists today. It fills the entire sky. We call it the cosmic microwave background, and it is the oldest light we can ever detect. It is a photograph of the universe at 380,000 years old, frozen in time. But here is what nobody tells you right away. When that light escaped, there was nothing left to make new light. The hydrogen was neutral now, cold, stable. Gravity was slowly pulling it together into enormous clouds, but nothing had ignited yet. No star had ever burned. No galaxy had ever formed. The universe went dark. Completely, totally dark. Astronomers call this period the cosmic dark ages, and it lasted somewhere between 100 and 200 million years. To put that in perspective, if the entire history of Earth were compressed into one day, the dark ages alone would last about 6 hours of total blackness in the middle of it. During this time, something was happening that you could not see. Gravity, the slowest and most patient force in nature, was doing its work. Those clouds of neutral hydrogen were drifting together. Slowly, over millions of years, the densest regions pulled in more and more gas. The clouds grew heavier. They collapsed inward under their own weight. Nothing exploded. Nothing flashed. But deep inside those invisible clouds, something was building toward a pressure that the universe had never seen before. And one more thing was happening during the darkness that most people never consider. The neutral hydrogen was not just sitting there passively. It was acting like a wall. Any ultraviolet light that managed to appear would have been instantly absorbed. The neutral hydrogen fog was so thick and so widespread that even if a single patch had briefly lit up, the light would have been swallowed before traveling any meaningful distance. The universe was not just dark. It was locked, sealed, a black room with the door shut from every direction. For over 100 million years, nothing changed that. Nothing escaped. But somewhere inside one of those collapsing clouds, the pressure was reaching a breaking point. Something was about to catch fire for the very first time in the history of the universe. And when it did, it would be nothing like any star you have ever imagined. Imagine a room where every surface is on fire. The walls, the ceiling, the floor, the air itself. That was the early universe. Not a metaphor. The temperature in the first seconds after the Big Bang was so extreme that the entire concept of matter barely applied. Particles formed and were instantly destroyed. Energy was everything. Then the universe began to expand, and as it expanded, it cooled. This cooling was not fast by human standards. It took 380,000 years. But in cosmic terms, that is almost nothing. The universe went from a temperature of trillions of degrees down to a few thousand degrees, roughly the surface temperature of a dim red star today. At that point, something irreversible happened. Electrons, which had been flying free and smashing into photons constantly, slowed down enough to be captured by protons. The two combined. Neutral hydrogen atoms formed across the entire observable universe in a relatively short window of cosmic time. Scientists call this recombination, which is actually a slightly misleading name, because protons and electrons had never been combined before. It was the first time, not a reunion. The moment neutral atoms formed, the universe became transparent. Light could travel freely. That ancient light flew outward and became the cosmic microwave background we can still detect today, confirmed, measured, mapped in extraordinary detail by satellites including WMAP and Planck. But here is where the story takes a dark turn. Literally, before recombination, the universe was opaque, but it was glowing. After recombination, it was transparent, but there was almost nothing left to glow. The light from the fireball was gone, spreading outward and cooling into microwaves. The hydrogen was neutral and cold. No stars had formed yet. The universe went from an inferno to a void. No new photon was being created anywhere. If you could have floated in space during this period with perfect eyes that could see all wavelengths of light, you would have seen nothing. Total blackness in every direction. Now here is something that sounds impossible but is confirmed physics. During the Dark Ages, the universe was actually more uniform than it is today. Every cubic foot of space looked nearly identical to every other cubic foot. There were tiny differences in density, regions slightly denser than others by about 1 part in 100,000. Those tiny ripples were the seeds of everything, every galaxy, every star, every planet, every atom in your body. But at the time, they were invisible. They were just slightly heavier patches of darkness. Gravity was the only force still actively doing anything. It was pulling those denser patches inward, very slowly, while the rest of the universe continued to expand around them. There was no light to see by, no heat to feel, no sound, because sound needs matter dense enough to carry it, and space was already thinning out. Just cold gas, gravity, and time. The universe had built a perfect stage, completely empty, completely dark, and 100 to 200 million years into this silence, the first cloud of hydrogen finally collapsed far enough. The pressure at its core reached a threshold that had never been reached before in the history of existence. Nuclear fusion ignited. A star was born. Nobody was there to see it. There was no one anywhere in the universe yet. But the darkness ended in one tiny spot, and that single point of light set off a chain reaction that would eventually, billions of years later, lead to telescopes, scientists, and a species asking how it all began. Keep that image in your head. One light in a universe of total darkness. Because the story of how that light spread is stranger than you expect. Neutral hydrogen is the simplest thing in the universe. 1 proton, 1 electron. That is the entire atom. It weighs almost nothing. It is invisible to the naked eye, and yet for hundreds of millions of years, it held the entire universe hostage. To understand why, you need to understand what neutral means in this context. When hydrogen is ionized, its electron has been ripped away. The proton is left with a positive charge, flying free. Ionized hydrogen is almost invisible to most light. Photons pass through it easily. That is why the universe today, filled with ionized hydrogen gas between galaxies, is largely transparent. Neutral hydrogen is different. The electron is still attached, and neutral hydrogen has a specific appetite. It absorbs ultraviolet light, particularly a wavelength called Lyman alpha, with almost perfect efficiency. Lyman alpha photons are the type produced when hydrogen atoms release energy When a Lyman alpha photon runs into a neutral hydrogen atom, the atom absorbs it almost instantly. In the early universe, the intergalactic medium, the gas filling the space between everything, was almost entirely neutral hydrogen. Confirmed, there were no galaxies yet, no quasars, no sources of ultraviolet radiation strong enough to ionize it. The neutral hydrogen covered everything like a blanket with no gaps. A single Lyman alpha photon released in that environment would travel a tiny distance before being swallowed. Scientists estimate that in the deepest part of the Dark Ages, a photon of that wavelength could travel less than 1 light-year before being absorbed. The observable universe is tens of billions of light-years across. The fog was essentially impenetrable. This matters enormously for the discoveries we will get to shortly, because 2 of the most astonishing galaxies ever found are visible from over 13 billion light-years away, and both of them are producing Lyman alpha light. That should be physically impossible given the fog. The fact that we can see them means something radical had already happened around them, but we are getting ahead of ourselves. During the Dark Ages, the neutral hydrogen fog did something else that is easy to miss. It prevented any early structure from being seen, even if you had a perfect telescope. There was simply no light to detect. The hydrogen was not emitting. It was not reflecting. It was cold and dark and absorbing anything that dared to pass through it. Think of it like trying to see the bottom of a lake that is covered in black ice, wrapped in fog, at midnight, with no flashlight, except the lake is billions of light years wide. The fog was not uniform though. Gravity was slowly pulling the hydrogen into denser clumps, and slightly less dense regions were thinning out. The structure of the universe was being written in hydrogen, invisible to any observer. When the first stars finally ignited, they began bombarding the surrounding gas with ultraviolet radiation. The neutral hydrogen immediately started absorbing it, but the stars were powerful enough that they ionized a small bubble around themselves, a tiny clear patch in an endless fog. Those bubbles were the beginning of the end for the Dark Ages. And here is the part that keeps astronomers awake. We still do not fully understand how those bubbles grew, how fast they expanded, whether they overlapped quickly or slowly. The details of how the universe went from completely fogged to completely clear is one of the biggest open questions in all of science. What we do know is that something had to punch those holes first. And the first thing to do, it was unlike anything that exists today. Gravity never stops. It does not need light to work. It does not need heat. It operates silently, invisibly, across any distance, pulling anything with mass toward anything else with mass. During the Dark Ages, when the universe was a cold black void, gravity was the only thing doing anything at all, and it had a blueprint to work from. Those tiny ripples in density from the early universe, regions slightly heavier than their surroundings by about 1 part in 100,000, became the targets. Gravity pulled neighboring gas toward the denser spots. The denser spots grew heavier, which made them pull harder. A slow, accelerating collapse began across the entire universe simultaneously, in millions of locations at once. Scientists call the structures that form dark matter halos. Here is the key idea. Most of the mass in the universe is not hydrogen. It is dark matter, a confirmed but still mysterious substance that does not interact with light at all. Dark matter started clumping first, because it was not affected by the pressure that kept regular gas spread out. It formed an invisible skeleton, a web of filaments and clumps, and the hydrogen gas followed, falling into the gravitational wells the dark matter had already dug. The first dark matter halos were not large. The earliest ones that could eventually form stars were roughly the mass of 1 million suns, crammed into a space far smaller than the Milky Way. Scientists call them mini-halos, and they began forming somewhere around 100 million years after the Big Bang. This is confirmed by simulations calibrated to CMB data, though the exact timing carries some uncertainty. Inside a mini-halo, the gas fell inward and heated up as it compressed. Heating gas causes it to push back outward, fighting the collapse. For a long time, these two forces, gravity pulling in, gas pressure pushing out, were nearly balanced. The collapse stalled, then the hydrogen began to cool. Molecular hydrogen, two hydrogen atoms bonded together, can radiate heat away as infrared light. As the gas cooled, the pressure dropped, and gravity won again. The collapse resumed. The gas fell deeper and faster. The core grew denser and hotter. This was the first factory, the first place in the universe where conditions were approaching what was needed to ignite nuclear fusion. It was not dramatic from the outside, just an invisible ball of gas, getting smaller and hotter in total darkness. Millions of these collapses were happening across the universe at roughly the same time, not simultaneously in a single moment, but within the same broad window of cosmic history. The universe was setting fires everywhere at once, all of them still hidden inside collapsing clouds, all of them racing toward a threshold. And the structures those collapses built were not gentle. The first halos merged with each other. Smaller ones fell into larger ones. The web of dark matter grew more complex. Gas streamed along invisible filaments and pooled at the intersections. The universe was building something it had never built before. And when the cores of those collapsing clouds finally crossed the line, what ignited was so extreme, so violent, so different from anything alive today, that if you saw one in the night sky, it would be visible from the other side of the observable universe. The wait was almost over. Somewhere between 100 and 200 million years after the Big Bang, a cloud of hydrogen and helium collapsed far enough. The core reached a temperature of about 18 million degrees Fahrenheit. Nuclear fusion switched on. The first star in the history of the universe was born. There was no one to see it. No planets existed yet. No eyes existed anywhere. But the universe changed forever in that moment. These first stars have a name, population 3 stars. Scientists have never directly observed one. Their existence is confirmed by theory and indirect evidence, but no telescope has yet captured one. They are like footprints we can see without having seen the feet that made them. Here is what made them extraordinary. Every star that exists today, including our Sun, formed from gas that had already been enriched by previous stars. Our Sun contains oxygen, carbon, iron, silicon, and dozens of other elements, all forged in the cores of earlier stars that died and scattered their material across space. The Sun is a third-generation star at minimum. Population 3 stars had none of that. The gas they formed from was almost pure hydrogen and helium, exactly what the Big Bang produced. No carbon, no oxygen, no heavy elements at all. Scientists call everything heavier than helium a metal, and these stars had essentially zero metal content. That one difference changed everything about them. Heavy elements in a star's gas act as a cooling agent. They help the collapsing cloud shed heat faster, which lets the cloud fragment into smaller clumps, which produces smaller stars. Without those cooling agents, the collapsing clouds stayed hotter and did not fragment as easily. They kept falling inward and building up mass. The result was stars of almost unimaginable size. Current models, confirmed by simulations and indirect evidence, suggest population 3 stars were between 100 and 1,000 times the mass of our Sun. Some theoretical models push that upper limit even higher. Our Sun is already 865,000 miles across. Imagine a star 300 times more massive, a sphere so large that if you placed it where our Sun sits, it would swallow Mercury, Venus, Earth, Mars, and extend well past the asteroid belt. These monsters burned at temperatures far hotter than anything alive today. They shone with ferocious intensity. A single one of them may have released more ultraviolet radiation in its short life than thousands of stars like our Sun. And their lives were very short. The bigger a star, the faster it burns through its fuel. Our Sun will last about 10 billion years total. A population 3 star, a few hundred times more massive, would burn through its core in about 2 to 3 million years. In cosmic terms, that is barely a blink. But during those few million years, each one blasted ultraviolet radiation outward in every direction. That radiation began ionizing the surrounding neutral hydrogen. Small bubbles of clear, ionized space formed around each star, like a lamp punching through fog. For the first time in hundreds of millions of years, there was light in the universe. But the story of what happened next, what these titans did when they ran out of fuel, is where things get genuinely extreme, because their deaths were even more violent than their lives. Scientists are certain population 3 stars existed. The math demands it. The observations confirm the chemical fingerprints they left behind, and yet not one has ever been directly seen. Every telescope ever built, including the most powerful one humanity has ever launched into space, has come up empty. That is not a failure of technology. It is a consequence of physics. Population 3 stars burned fast. The largest ones lived only 2 to 3 million years before dying in catastrophic explosions. By the time the universe had aged enough for light to have any hope of reaching us from those first galaxies, every single population 3 star had already died. They are gone, completely gone. Nothing from that generation survives today. What we have instead are their chemical signatures. When these stars died, they scattered heavy elements into the surrounding gas. Elements like carbon, oxygen, magnesium, and iron, forged in their cores through nuclear fusion, were blasted outward. The next generation of stars formed from that enriched gas. Then those stars lived and died and enriched the gas further. Every generation added more metals. By the time you reach our sun, born about 4.5 billion years ago, the gas was rich with dozens of elements. Astronomers can trace this enrichment backward like tree rings. By studying the chemical makeup of the oldest surviving stars in our galaxy, stars called Population 2, they can infer what the gas looked like before them. And when they push the math back far enough, they reach a starting point of almost pure hydrogen and helium. Population 3 is the logical predecessor that the chemistry demands existed. But there is another clue, one still being pieced together by researchers today. Certain galaxies observed by the James Webb Space Telescope show chemical compositions that do not match any standard model of stellar evolution. Elevated nitrogen, unusual ratios of elements, patterns that some researchers believe may be the faint echo of Population 3 stellar deaths mixed into the gas of the very earliest galaxies. One of those galaxies is the most distant object ever confirmed. We will get there. Now, here is the detection problem laid out simply. Population 3 stars were bright, but they existed at redshifts above 15, meaning their light has been stretched by cosmic expansion to such extreme infrared wavelengths that even Webb struggles to detect individual stars. What Webb can potentially detect is not a single Population 3 star, but a galaxy dominated by them, where thousands or millions of these monsters are burning simultaneously, and their combined light is strong enough to register on Webb's instruments. So far, no galaxy has been confirmed as purely Population 3 dominated. Several candidates exist. All remain under investigation. This is an open scientific question, confirmed unknown. The closest thing we have found are galaxies at the very edge of the observable universe, showing chemical compositions that hint at Population 3 involvement. And 2 of those galaxies are at the center of this entire story. The first galaxies Webb found that broke every prediction were not calm, quiet places. They were violent, blazing, chemically strange objects formed in conditions that left scientists scrambling for explanations. And buried inside some of them may be the last traces of the universe's original fire. Something Webb keeps almost catching a glimpse of, just never quite directly, until the discoveries that changed everything came in, one after another. A Population 3 star lived fast and burned hard. Its death was proportional. Stars in the 100 to 250 times the mass of our sun range did not die quietly. When they exhausted their nuclear fuel, their cores collapsed almost instantaneously. The outer layers fell inward and then bounced back outward in an explosion called a core collapse supernova. These were among the most energetic events in the history of the universe. each one releasing more energy in a few seconds than our Sun will emit in its entire 10 billion year life. But for the very largest population 3 stars, above about 250 solar masses, something even more extreme happened. Their cores collapsed so completely and so fast that the explosion could not fully escape. Instead of scattering material across space, much of the star collapsed directly into a black hole. These are called direct collapse black holes, and they are one of the leading candidates for the seeds of the supermassive black holes found at the centers of nearly every large galaxy today, including ours. Think about that chain of events. A star forms from pure hydrogen in the darkness. It burns for 2 million years. It dies and either scatters heavy elements across space or collapses into a black hole the size of a city with the mass of tens of thousands of suns. And then that black hole begins feeding on surrounding gas and growing. The ones that exploded did something equally important. When a population 3 supernova detonated, it did not just release energy, it launched heavy elements, carbon, oxygen, silicon, iron, outward at millions of miles per hour. Those elements mixed into the surrounding neutral hydrogen gas. The next cloud that collapsed to form stars was no longer pure hydrogen. It had been seeded. That seeding made the second generation of stars smaller, cooler, and longer lived. Some population 2 stars formed over 13 billion years ago and are still burning today in the outer halo of the Milky Way. Astronomers study these ancient survivors as living fossils of the early universe. But the supernovae did something else, something that matters for the story of the first light. The explosion sent a shockwave outward through the surrounding gas. That shockwave compressed some nearby gas, triggering new star formation. It also drove ionized material outward, helping to expand the bubble of ionized hydrogen that the original star had been carving out during its life. Each population 3 death, then, was not an ending. It was a trigger. It enriched the next generation of stars. It seeded black holes. It pushed ionization further into the neutral fog. The universe was running a relay race. Each generation of stars handed something to the next. Heavier elements, larger bubbles of clear space, more powerful black holes, and somewhere in this relay, the first galaxies were forming. Collections of stars bound together by gravity, growing from mergers and gas accretion. Their combined ultraviolet output finally powerful enough to start doing something truly dramatic to the universe around them. The fog was beginning to clear. The question is, when did that clearing start? And how fast did it happen? Those are questions that stumped astronomers for decades, until a telescope showed them something they were not prepared to see. Reionization is the process that ended the cosmic dark ages. It is how the universe went from a black, opaque fog of neutral hydrogen to the clear, transparent cosmos we live in today. And it is one of the most dramatic transformations in the history of everything. Here is the basic picture. When the first stars and galaxies ignited, they released ultraviolet radiation. That radiation slammed into the surrounding neutral hydrogen. When a UV photon hits a neutral hydrogen atom with enough energy, it knocks the electron free. The atom becomes ionized. That single ionized hydrogen atom can no longer absorb Lyman alpha light. The fog thins slightly. Now scale that up to millions of stars inside a single early galaxy, all firing UV radiation outward continuously. The gas immediately surrounding the galaxy gets ionized. A bubble of clear space forms. Inside the bubble, light can travel freely. Outside the bubble, the neutral fog still blocks everything. The bubbles grew. As galaxies formed and burned brighter, their ionized bubbles expanded outward, eating into the surrounding fog like a lit match held to tissue paper, slowly at first, then faster as the bubble grows and the star formation inside the galaxy accelerates. Then something even more powerful happened. Neighboring galaxies had their own bubbles. As the universe aged and galaxies multiplied, the bubbles began touching each other, then overlapping, then merging into larger and larger regions of ionized space. At some point, the connected ionized regions became bigger than the remaining neutral patches. The fog stopped being a single solid barrier and became isolated islands. Then those islands shrank, then they disappeared. The universe became fully transparent. Reionization was complete. Under old models, built before the James Webb Space Telescope launched, this process was estimated to have finished about 1 billion years after the Big Bang. The evidence for that estimate came from studying quasar light. Quasars are extremely bright objects powered by supermassive black holes. Their light passes through intergalactic gas on its way to us. By analyzing which wavelengths got absorbed, scientists could map where neutral hydrogen still existed along the line of sight. Those measurements suggested a fully ionized universe by about 1 billion years after the Big Bang, confirmed under the pre-Webb model. But here is what nobody expected. Webb started finding galaxies that were already producing Lyman alpha emission deep inside the dark ages, hundreds of millions of years before reionization was supposed to be anywhere near complete. The bubbles were forming earlier, much earlier. Some galaxies had apparently punched through the fog so effectively that their light was escaping from a period when the surrounding universe was still dominated by neutral hydrogen. That should have been impossible. The old timeline was wrong. How wrong, exactly, was just beginning to become clear, and the implications reached far beyond a simple calendar correction. What Webb found suggested that the very engines driving reionization were different from what anyone assumed. Nobody was there to observe the Dark Ages. No instrument existed. No civilization existed anywhere in the universe. So how do scientists know with confidence that the cosmos was once a cold, lightless void for hundreds of millions of years? The answer is that the universe left evidence everywhere. You just have to know where to look. The first piece of evidence is the cosmic microwave background. When neutral hydrogen formed during recombination, photons that had been trapped were released all at once. That light has been traveling and cooling ever since. Today, it fills the entire sky as microwave radiation with a temperature of about -454 degrees Fahrenheit, just barely above absolute zero. Satellites have mapped it in extraordinary detail. It shows a universe that was smooth, hot, and structureless at 380,000 years old. Confirmed, this is the last snapshot before the Dark Ages began. The second piece of evidence comes from quasar spectra. Quasars are so bright, they can be seen from almost any distance. Their light passes through billions of light years of intergalactic gas before reaching our telescopes. Scientists analyze which wavelengths are absorbed along the way. Neutral hydrogen leaves a very specific absorption signature. By studying quasars at different distances, meaning different times in cosmic history, astronomers can track when and where neutral hydrogen still existed in the intergalactic medium. This technique is called the Lyman alpha forest, and it directly confirmed the existence of a period of high neutral hydrogen density in the early universe. Confirmed. The third piece of evidence is the absence of early galaxies before Webb. Every telescope before Webb had a hard distance limit. Beyond a certain redshift, nothing was detectable. That absence was consistent with a period of no luminous structure, the Dark Ages predicted by theory. The boundary where galaxies started appearing matched the predictions for when the first stars were expected to have formed. The fourth piece of evidence is chemical. The oldest surviving stars in our galaxy, population 2 stars, have almost no heavy elements. Their composition is consistent with forming from gas that had only been through 1 or 2 rounds of stellar enrichment. That points to them being formed not long after the very first stars, placing the first stellar generation firmly in the period after the Dark Ages ended. None of these 4 lines of evidence alone would be conclusive. Together, they form a picture that is extremely robust. The Dark Ages happened. They lasted between 100 and 200 million years following recombination. They ended when the first stars and galaxies ignited and began ionizing the surrounding gas. That picture held for decades. It was the foundation of modern cosmology. Webb did not knock that foundation down. What Webb did was far more interesting. It showed that things happened inside that framework much faster, much more dramatically, and much earlier than anyone predicted. The timing was wrong, the brightness was wrong, the chemistry was wrong, and the galaxy that shattered the prediction about when reionization began is one we have not fully explained yet. There is a photograph of the universe at 380,000 years old. It covers the entire sky. It was taken automatically, by physics itself, and we have been able to read it with satellites for decades. It is called the cosmic microwave background, and it is the single most important piece of evidence in all of cosmology. Here is how it works. In the early universe, matter and energy were coupled together. Every photon of light was constantly bouncing off free electrons, getting scattered, unable to travel in a straight line for any significant distance. The universe was like a thick fog where light diffused in every direction at once. This went on for 380,000 years. Then recombination happened. Electrons bonded with protons. The fog cleared. The photons that had been scattering endlessly were suddenly free. They shot outward in all directions simultaneously from every point in space. That burst of light is what we call the cosmic microwave background. Here is the remarkable part. That light has been traveling ever since. It has never stopped. It fills the entire observable universe, arriving at Earth equally from every direction in the sky. When you point a sensitive microwave detector at any part of the sky, you are seeing light that last scattered off matter 13.4 billion years ago. But it has changed along the way. As the universe expanded, the wavelengths of those photons stretched. Light that was originally visible and infrared has been stretched all the way into microwave wavelengths. The temperature of the CMB today is about -454 degrees Fahrenheit. It is the coldest known natural radiation field in the universe. Confirmed, the CMB is almost perfectly uniform. In every direction, it has almost exactly the same temperature, but almost is the key word. There are tiny variations, about 1 part in 100,000, slightly warmer or cooler patches spread across the sky. Those tiny variations are the seeds of everything. They represent the slightly denser and slightly less dense regions of the early universe that gravity later amplified into galaxies, galaxy clusters, and the large-scale structure of the cosmos. Satellites, including COBE, WMAP, and most recently Planck, have mapped these temperature variations in extraordinary detail. The pattern of those variations tells scientists the age of the universe, its composition, the ratio of ordinary matter to dark energy, and the geometry of space itself. The CMB is the single most information-rich observation in all of astronomy, and it draws a hard line in time. It shows us the universe just before the Dark Ages began. Everything after that, for the next 100 to 200 million years, is a gap, a period we can only reconstruct from theory and indirect clues. Webb was built, in part, to start filling that gap, to find the first light that followed the darkness. And what Webb found on the other side of that gap was not what anyone expected. The universe had apparently started doing things far earlier than the CMB's own predictions suggested it should. The Hubble Space Telescope is one of the greatest scientific instruments ever built. Since its launch in 1990, it has changed astronomy permanently. It has measured the expansion rate of the universe. It has photographed galaxies that formed billions of years ago. It found evidence for dark energy. It gave us images of cosmic structures that rewrote textbooks, and it was completely blind to the earliest galaxies. This was not a flaw, it was physics. Here is the problem. The universe is expanding. It has been expanding since the Big Bang. As space stretches, it carries light with it. Light traveling through expanding space gets its wavelength stretched, shifting it toward the red end of the spectrum. The farther away the source, the more expansion the light has traveled through, the more it gets stretched. This is called redshift. A galaxy that existed 400 million years after the Big Bang is so far away that its light has been traveling for over 13 billion years. Over that time, Space has expanded so dramatically that the light originally emitted in the ultraviolet has been stretched all the way into the infrared. Ultraviolet light has wavelengths far too short to see. Infrared has wavelengths far too long to see. But in between is visible light, the narrow range our eyes and most camera sensors detect. Hubble's cameras were optimized for visible and ultraviolet light. Its infrared capability existed, but was limited. The most sensitive infrared detector on Hubble, the wide-field camera 3 infrared channel, could detect wavelengths up to about 1.7 micrometers. The earliest, most redshifted galaxies, from the first few 100 million years after the Big Bang, have their light stretched to wavelengths of 2 micrometers and beyond. Hubble simply could not reach there. Technically, thermally, optically, it was out of range. The farthest galaxy Hubble ever confirmed was seen at about 400 million years after the Big Bang. That was essentially Hubble's hard limit. Beyond that, the infrared wavelengths exceeded what its instruments could detect with any reasonable sensitivity. The earliest galaxies were invisible to it, not because they were too faint, but because their light had been shifted into a range Hubble could not properly see. To reach them, a telescope needed to be built specifically for the infrared. It needed to be kept extraordinarily cold, because warm instruments emit their own infrared radiation that would drown out the faint signals from distant galaxies. And it needed a much larger mirror to collect enough of the extremely faint, extremely redshifted light. That telescope took 3 decades to design, build, and launch. It cost $10 billion. It required the cooperation of space agencies across 3 continents. It was placed nearly 1 million miles from Earth, far beyond any hope of astronaut repair. And when it opened its eye for the first time in 2022, it immediately began showing scientists things that made them question everything they thought they knew. The plan for the James Webb Space Telescope began forming in the 1990s. Astronomers knew Hubble's limits. They knew the earliest galaxies were hiding in the infrared, and they knew that to see them, they needed a telescope purpose-built for that task. What they designed over the following 2 decades was unlike anything that had come before. The first challenge was the mirror. A bigger mirror collects more light. More light means the ability to detect fainter objects. For the early universe, faint is the operating word. These galaxies are 13 billion light-years away, and the light reaching us from them has been traveling and spreading out for billions of years. By the time it arrives at a telescope mirror, only a tiny handful of photons per second are hitting any given square foot of surface area. Webb's primary mirror spans 21 feet across, about 2.5 times the diameter of Hubble's. But mirror area scales with the square of the diameter, so Webb collects more than 6 times as much light as Hubble per unit of time. That is 6 times more photons from every distant galaxy, which translates directly into the ability to detect things Hubble never could. The mirror is made of 18 hexagonal segments, each coated in a microscopically thin layer of gold. Gold reflects infrared light more efficiently than any other common coating material. Each segment can be individually adjusted to align with the others down to a precision of about 1/20,000th the width of a human hair. Confirmed. The alignment process took months after launch and worked essentially perfectly. The second challenge was temperature. Infrared light is essentially heat radiation. Any warm object, including the telescope itself, emits infrared light. If Webb's instruments were anywhere near room temperature, they would be drowning in their own infrared glow, completely unable to see the faint signals from distant galaxies. Webb carries a sunshield the size of a tennis court, 5 layers of a material called kapton, each thinner than a human hair. The shield keeps the telescope's instruments at about -387 degrees Fahrenheit, cold enough to suppress virtually all self-generated infrared noise. Some of Webb's detectors operate even colder than that. The third challenge was location. Hubble orbits Earth at about 340 miles up, close enough for astronauts to have repaired it multiple times. Webb orbits at a gravitational balance point called L2, nearly 1 million miles away. At that distance, no repair mission is possible. Everything had to work perfectly the first time. It launched on the 25th of December 2021. It unfolded in space over the following weeks in one of the most nerve-wracking sequences in space exploration history. 344 individual steps that all had to succeed. Every single one did. And in the summer of 2022, it began returning data. Within months, the first results were already threatening to overturn decades of established cosmology. The mirror had done its job. What it was showing scientists was something they had not built equations for. Light is not just what you see. Visible light, the colors from red to violet, is a tiny slice of a much wider spectrum. Radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, all of these are the same thing, electromagnetic radiation. They differ only in wavelength. The human eye evolved to detect the wavelengths most abundant in sunlight at Earth's surface. That is why we see visible light. But the universe communicates in every wavelength, and some of the most important information it carries arrives in the infrared. Here is why infrared matters for studying the early universe. When a galaxy forms stars, those stars emit mostly ultraviolet and visible light. For a galaxy close to us, that light travels a short distance and arrives at our telescopes still in its original wavelength range. We can see it with ordinary instruments. But for a galaxy formed 300 million years after the Big Bang, the situation is completely different. That galaxy is so far away that the universe has expanded dramatically since the light left it. The expansion stretches the light's wavelengths proportionally to how much space itself has expanded. For the most distant galaxies, Webb is now finding, the expansion factor is more than 14. Light that left as ultraviolet arrives as mid-infrared. This means the entire visual story of these ancient galaxies is encoded in infrared wavelengths between 1 and 5 micrometers, completely invisible to human eyes, completely beyond Hubble's reach, but right in the sweet spot for Webb's instruments. Webb has 4 main science instruments. 2 of them, NIRCam and NIRSPEC, cover the near-infrared range and are the primary tools for finding and confirming ancient galaxies. NIRCam, the near-infrared camera, takes deep images. Scientists point it at a patch of sky and let it collect light for many hours. The resulting image shows thousands of galaxies at once, each one a different color in the infrared, each color corresponding to a different distance and redshift. Galaxies at extreme distances have a specific feature that makes them identifiable even in images alone. They disappear completely at wavelengths shorter than a certain threshold because the neutral hydrogen along the line of sight absorbs all that short wavelength light. A galaxy that shows up in longer infrared bands but is completely absent in shorter ones is likely a very distant candidate. To confirm distance, NIRSPEC takes over. It splits the light from a target galaxy into a spectrum and looks for specific emission or absorption lines. These lines, produced by specific atoms at specific wavelengths, act like fingerprints. By measuring how far those fingerprints have shifted from their known rest wavelengths, scientists calculate the redshift precisely, and from that the distance and the age of the universe when the light was emitted. This is how Webb confirmed the galaxies at the edge of observable space. Image first, spectrum second. And the spectra Webb has returned from the deepest galaxies it has found contain surprises that no model predicted. Imagine standing on a train platform as a train blows its horn and speeds past you. When the train is approaching, the sound waves compress, and the horn sounds higher pitched. When the train passes and moves away, the sound waves stretch, and the horn drops to a lower pitch. This is the Doppler effect, and it works for light too. But the redshift of distant galaxies is not exactly the Doppler effect. It is something stranger. The galaxies are not moving through space the way a train moves through air. The space itself is stretching, and as space stretches, any light traveling through it gets stretched along with it. Picture light as a wave drawn on a rubber band. Stretch the rubber band and the wave gets longer. longer wavelengths of light are redder. So light from a distant galaxy, originally emitted at blue or ultraviolet wavelengths, arrives at our telescopes shifted toward red and beyond, into the infrared. The amount of stretching depends directly on how much the universe has expanded since the light was emitted. Scientists express this as a redshift number, abbreviated Z. A redshift of 1 means the universe was half its current size when the light left. A redshift of 2 means the universe was 1/3 its current size. A redshift of 13, like the galaxy we will talk about shortly, means the universe was only about 1/14 its current size when that light departed. At a redshift of 13, visible light has been stretched so far that it arrives as mid-infrared radiation. A wavelength of about 0.12 micrometers, deep ultraviolet becomes 1.7 micrometers, well into the infrared. Every photon from that galaxy has been transformed during its journey. The redshift number also tells us directly how old the universe was when the light was emitted. Cosmologists use the measured expansion history of the universe to convert redshift into a time. At Z equals 13, the universe was about 330 million years old. At Z equals 14.4, the universe was about 280 million years old. These numbers are confirmed by our best cosmological models. Redshift is also what makes certain objects invisible to Hubble, but visible to Webb. Hubble's detectors are most sensitive below 1.7 micrometers. Webb's detectors extend from about 0.6 to 28 micrometers. The most distant galaxies Webb has found have their brightest emission lines landing squarely in the range Webb can see and Hubble cannot. There is one more thing redshift reveals that matters here. As light gets stretched, it also gets dimmed. The energy of a photon is proportional to its frequency, which decreases as the wavelength grows. A photon that lost 93% of its original wavelength through cosmic expansion also lost most of its energy. By the time it reaches Webb, it is carrying a tiny fraction of the punch it started with. The fact that Webb can detect these faint, stretched, ancient photons at all is a tribute to its engineering, and the signal it picked up from the galaxy at the edge of our observable universe is even more puzzling in context. That galaxy should have been invisible for more reasons than just distance. Webb released its first full science images in July 2022. The astronomical community had been waiting decades for this moment. The images were stunning, but within weeks, the data they contained began creating a crisis that nobody had planned for. The problem was not what Webb failed to see. It was what Webb saw that it should not have. Before launch, cosmologists had used their best models of galaxy formation to predict what Webb would find at different distances and redshifts. These predictions were based on the Lambda CDM framework, the standard model of cosmology, which describes a universe dominated by cold, dark matter and dark energy. Under this model, galaxy formation in the early universe should have been a slow, gradual process. The earliest galaxies should have been small and faint. Bright, massive galaxies should have taken billions of years to build up. Webb looked at small patches of sky and immediately began finding galaxies in the first few 100 million years after the Big Bang that were far too bright. Galaxies with masses and luminosities that the models said should not exist until much later. Galaxies that appeared to have formed stars at rates impossible to explain with standard physics under standard timelines. One early estimate, which caused significant discussion in the community, suggested that some of these candidate galaxies had masses comparable to the Milky Way, but existed when the universe was only a few 100 million years old. If true, that would mean those galaxies had assembled their entire stellar mass in a fraction of the time the models allowed. Astronomers were careful to note that early photometric estimates, color-based guesses at distance without spectroscopic confirmation, can be wrong, and some early extreme candidates were later revised downward, but the general pattern survived. Confirmed spectroscopically, Webb is finding roughly 100 times more bright galaxies in the early universe than pre-launch models predicted. Confirmed, this was not a small discrepancy. A factor of 100 is not a rounding error. It is a signal that something fundamental was either missing from the models or wrong about them. The debate began immediately. Some researchers argued the standard cosmological model needed revision. Others argued the models were fine, but the astrophysics of early star formation was simply more extreme than anyone had accounted for. Others pointed to observational effects. Maybe dust was playing a different role at high redshift, or maybe the galaxies were being seen at unusually active moments. The most striking individual discoveries came later. Two galaxies in particular cut through the noise and demanded an answer. One was glowing from 330 million years after the Big Bang with a type of emission that should have been swallowed by the surrounding universe. The other was the farthest confirmed object in the history of human observation. Both of them broke the rules in different ways, and the rules they broke are not minor footnotes. They are the foundation of how we thought the early universe worked. The galaxy has a name that sounds like a filing system: JWST, Z131, LA. Translated, JWST refers to the survey it came from, the JWST, Advanced Deep Extragalactic Survey. The Z13 refers to its redshift of 13.01. The LA at the end stands for Lyman Alpha, which is exactly the detail that makes this galaxy extraordinary. Let us start with what it is. A galaxy, a collection of stars, gas, and dust held together by gravity, existing 330 million years after the Big Bang. At that moment, the universe was only 2.5% of its current age. The Milky Way did not yet exist in any recognizable form. The Sun would not form for another 9.5 billion years. Our planet would not form for another 10 billion years. Jade's GS Z131 LA was already there, already burning, already producing enormous amounts of ultraviolet radiation. The galaxy was found using NIRCam during deep imaging of a region of sky called the Good South Field, one of the most intensively observed patches in all of astronomy. Follow-up spectroscopy with NIRSpec required 18.7 hours of continuous observation time, staring at this single object across multiple nights of telescope time in January 2024. The results were published in the journal Nature on the 27th of March 2025, led by astronomer Joris Wittstock from the University of Cambridge and the University of Copenhagen. Confirmed. The spectroscopy revealed a clear Lyman alpha emission line, an equivalent width greater than 40 angstroms. That number matters. Before this discovery, Lyman alpha emission with that kind of strength had only been detected in galaxies at redshifts below 9, meaning from a time when the universe was at least 550 million years old and reionization was already well underway. This galaxy is producing that same signal from 220 million years earlier. The light from this galaxy has been traveling for about 13.4 billion years to reach Webb's mirror. Every photon that hit the detector left that galaxy before the Earth existed, before the Sun existed, before most of the stars in the Milky Way had formed. And yet, it is glowing with a signal that should have been invisible. At redshift 13, the intergalactic medium, the gas filling the space between galaxies, was dominated by neutral hydrogen. That neutral hydrogen absorbs Lyman alpha photons almost perfectly. A galaxy producing Lyman alpha light that deep in the dark ages should have had its signal completely swallowed before it traveled any appreciable distance. The signal was not swallowed. It made it across 13.4 billion light years. How is that possible? The answer has a name, but the answer raises even bigger questions. The Lyman alpha signal from JWST GS Z131 LA should not exist. That is the conclusion Joris Wittstock and his team arrived at after confirming the spectroscopy. The universe at redshift 13 was not supposed to let Lyman alpha photons travel any significant distance. The neutral hydrogen fog was too thick, too complete, too efficient at absorbing that exact wavelength. To understand why this is so strange, think of the Lyman alpha photon as a specific radio frequency, and the neutral hydrogen as a material that absorbs only that one frequency with almost perfect efficiency. If you tried to broadcast that frequency through a room completely filled with that absorbing material, the signal would die within a few feet. At redshift 13, the intergalactic medium was that room. Neutral hydrogen filled it completely. Any Lyman alpha photon produced inside a galaxy should have been absorbed within a tiny fraction of a light year. The observable universe is tens of billions of light years across. Reaching us from 13.4 billion light years away was supposed to be flatly impossible, and yet there it was. 40 angstroms of equivalent width, unambiguous, confirmed. The only explanation that fits is that the galaxy had already ionized a substantial bubble of hydrogen around itself, a region of space around JWST, Z13, LA, where the neutral gas had already been stripped of its electrons. Inside that ionized bubble, Lyman alpha photons could travel freely if the bubble was large enough and the photons could get far enough from the galaxy before hitting neutral gas again. The light could escape into the intergalactic medium and eventually reach us. Scientists modeled the minimum size of that bubble. Based on the strength of the detected signal, the surrounding universe would have needed to be at least 5% ionized at redshift 13 if this galaxy is representative of the broader population. Previous estimates had placed that ionization level much later in cosmic history. This galaxy pushed the confirmed onset of reionization back by approximately 270 million years compared to prior estimates. Confirmed, that is not a small revision. 270 million years is longer than the entire time-complex life has existed on Earth. So what created the ionized bubble? Two main candidates exist, and the science is not settled. The first possibility is intense star formation. If JWST Z13 LA was producing stars at an exceptionally high rate, those new stars, many of them hot and massive, would have flooded the surrounding gas with ultraviolet radiation. Given enough time and enough star formation, a galaxy can carve a substantial ionized region around itself. The second possibility is an active galactic nucleus, a supermassive black hole at the center of the galaxy, actively feeding and radiating enormous amounts of energy. Black holes accreting matter release intense radiation across many wavelengths, including ultraviolet, which would ionize the surrounding gas efficiently. Some spectral features in the galaxy's data hint at possible AGN activity, but the evidence is not conclusive. This remains an open and actively debated question. What is not debated is what this discovery means. Reionization started earlier than we thought. The first ionized bubbles appeared earlier. Something was already punching through the fog at 330 million years after the Big Bang, and it was doing so with remarkable power. But compared to what Webb found next, JWST Z13 LA looks almost close by. The most distant confirmed object in human history came from even deeper in the dark. Picture a lighthouse standing in the thickest fog you have ever seen. The fog is so dense that the light cannot travel more than a few feet before disappearing completely. But right around the lighthouse, the heat from the lamp slowly burns the fog away. A small, clear circle forms. Inside that circle, the light travels freely. Outside it, the fog is still solid. That is an ionized bubble. And JWST Z13 LA had already built one around itself at 330 million years after the Big Bang. Here is how it works in detail. The galaxy is producing ultraviolet radiation continuously from its hot, massive stars. That radiation flies outward in every direction. The nearest neutral hydrogen atoms absorb it and get ionized. Their electrons are stripped free. Those atoms can no longer absorb Lyman alpha light. A thin shell of ionized gas forms around the galaxy. But the galaxy keeps producing radiation. The shell keeps pushing outward. More neutral hydrogen gets ionized. The bubble grows. The rate of growth depends on two competing factors: how fast the galaxy is producing ionizing photons, and how fast the ionized hydrogen is recombining back into neutral atoms. In the dense early universe, recombination happened quickly, so the galaxy had to maintain a high output just to keep the bubble from shrinking. At some point, The bubble reaches a size where Lyman alpha photons produced inside the galaxy can travel to the bubble's edge, pick up enough velocity from the galaxy's own gas motions, and shift their wavelength just enough to avoid absorption when they cross into the neutral fog beyond. They escape. They travel across billions of light years. They hit Webb's mirror. The minimum bubble size needed to explain the detected signal from JWST Z131LA is substantial. Models suggest it extended at least several million light-years from the galaxy's center. To put that in perspective, the distance from the Milky Way to its nearest large neighbor, the Andromeda Galaxy, is about 2.5 million light-years. This bubble was larger than that gap. Carving a bubble that size in 330 million years requires an enormous sustained output of ionizing radiation, which raises the question again, what was powering it? A galaxy forming stars at a normal rate for its mass could not have built that bubble fast enough. Something was working at extreme intensity, either an unusually high rate of star formation, a massive black hole actively feeding and radiating, or some combination of both. Here is the detail that makes this even more striking. JWST Z131LA is not alone. Webb has found a small number of other galaxies also showing Lyman alpha emission at very high redshifts, each one implying its own ionized bubble. These bubbles were not evenly distributed, they clustered. Some galaxies appear to have been sitting near each other, their bubbles overlapping, creating larger connected regions of ionized space earlier than any single galaxy could have managed alone. The fog was not clearing uniformly from the outside in. It was being punched through from inside, from many directions at once, by the brightest and most active galaxies in the early universe. And the brightest of all the objects discovered so far in that era of darkness came from even earlier. It was named after a question. This is one of the most important unanswered questions in current astronomy, and the reason it matters goes far beyond a single galaxy. The distinction between star formation and a black hole as the power source for the ionized bubble changes everything about what we think happened in the early universe. Here is why. If intense star formation is responsible, it means early galaxies were simply forming stars at rates far higher than our models predicted. That is a problem for the models, but it is a solvable one. You adjust the equations, allow for more efficient gas collapse at early times, and the rest of the framework can largely survive. But if a supermassive black hole is doing the work, the implications are more dramatic. Supermassive black holes, the kind found at the centers of modern galaxies, are thought to grow slowly over billions of years through mergers and gas accretion. Finding one already massive enough to drive reionization in a galaxy that is only 330 million years old pushes the timeline of black hole growth to its absolute limit and possibly beyond. Under standard models, there simply has not been enough time at redshift 13 for a black hole to grow to the mass required to produce the observed radiation levels. Assuming it started from a population 3 stellar remnant and grew at the maximum theoretical rate. Some researchers argue this means the seeds of these black holes were larger than expected, possibly formed through the direct collapse of massive gas clouds rather than through stellar death. Others suggest the growth rates were periodically higher than the theoretical maximum, a concept that is itself contested. Examining the spectral data from JWST Z131LA, certain emission line ratios hint at conditions consistent with an active galactic nucleus. But those same ratios can also be produced by extremely hot, massive stars, the kind expected in a galaxy with zero or near zero metal content. The spectral fingerprints overlap. The data alone cannot yet distinguish between the two scenarios. This is a confirmed unknown. Current instruments cannot resolve it for objects at this distance and redshift. What scientists are doing now is building more detailed models of both scenarios and testing them against every measurable property of the galaxy. Its color, its brightness, its emission line widths, its estimated mass. Each property constrains the possibilities slightly. The most likely answer, based on current evidence, is that both processes are happening simultaneously. intense star formation, and an active black hole, each contributing to the radiation budget, together producing a bubble that neither alone could sustain. This is the leading working hypothesis, but it is still a theory, confirmed unknown. What is confirmed is the result. The bubble exists. The Lyman alpha signal escaped. Reionization was already underway at 330 million years after the Big Bang, and the object that proved the universe was doing extraordinary things even earlier arrived from a point in time so close to the beginning that it genuinely stretches the imagination. On the 16th of May 2025, astronomer Rohan Naidu pointed Webb's NIRCam at a specific region of sky and collected an image. Hidden in that image was a smudge of light so faint it required careful analysis to even identify as a galaxy. That smudge turned out to be the most distant confirmed object in the history of human observation. Its name is MOME Z14. The MOME stands for Mirage or Miracle, the name of the spectroscopic survey that followed up on it. The Z14 refers to its redshift of 14.44. Confirmed by spectroscopy published in the Open Journal of Astrophysics in January 2026. Let those numbers land for a moment. A redshift of 14.44 means the universe was only 280 million years old when this galaxy's light departed. The universe is estimated to be about 13.8 billion years old. MOME Z14 existed when the universe was 2% of its current age. The light that hit Webb's mirror had been traveling for approximately 13.5 billion years before it arrived. To put 280 million years in context, 280 million years ago on Earth, the first dinosaurs had not yet appeared. The supercontinent Pangaea had just begun breaking apart. Complex life on Earth was only about 300 million years old at that point, and MOME Z14 was already a fully formed, actively star-forming galaxy. The previous record holder was a galaxy called JWST, found at redshift 14.18, about 300 million years after the Big Bang. MOME Z14 pushed the frontier back another 20 million years. Small in absolute terms, but significant because each step closer to the Big Bang becomes exponentially harder to achieve. The universe was smaller, hotter, and the signals are fainter. Finding MOME Z14 required the full power of Webb's infrared sensitivity. Its light has been stretched so dramatically by cosmic expansion that it arrives primarily as mid-infrared radiation. The spectroscopic confirmation required detecting specific emission lines shifted far from their original wavelengths, each one a signature of the galaxy's chemical makeup and distance. The confirmation was unambiguous. The redshift of 14.44 places it definitively beyond anything ever confirmed before. But the distance alone is not what makes MOME Z14 scientifically important. What makes it extraordinary is what it looked like, what it was doing, and what was locked inside its chemistry. Because for an object that existed so close to the beginning of time, MOME Z14 made no sense at all. MOME Z14 is tiny, about 240 light-years across. To get a sense of that size, the Milky Way is roughly 100,000 light-years in diameter. MOME Z14 is about 400 times smaller than our galaxy. If the Milky Way were the size of a football field, MOME Z14 would be roughly the size of a playing card lying on it. Its mass is comparable to the Small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way that you can see with the naked eye from the southern hemisphere. Not particularly impressive by modern standards. And yet MOME Z14 is blazing. Its absolute ultraviolet brightness places it at about 1/10 the total luminosity of the entire Milky Way, from a galaxy 400 times smaller. That ratio is not just unusual, it is the kind of output that makes physicists check their calculations multiple times. Standard models of galaxy formation predict a relationship between a galaxy's mass and its brightness. More massive means more stars, means more light. A galaxy, the mass of the Small Magellanic Cloud, should produce a corresponding level of light. MOME Z14 produces roughly 100 times more than that prediction, confirmed by spectroscopic analysis. The explanation that fits best is extreme, concentrated star formation. MOME Z14 was apparently going through a violent burst of stellar birth. At the moment Webb observed it, compressing enormous amounts of gas into new stars at a rate far exceeding anything seen in galaxies of comparable mass in the modern universe. Every cubic light-year of this tiny galaxy was producing stars at a furious pace, each new star adding to the ultraviolet output. This connects to a broader phenomenon astronomers call bursty star formation, which is currently the leading explanation for why so many early galaxies appear brighter than models predict. Early galaxies did not build up their stellar populations gradually, the way the models assumed. They formed stars in violent, irregular bursts, periods of extreme activity separated by quieter phases. During a burst, a galaxy can briefly outshine anything its mass would suggest, by a factor of 10, 50, or even 100. If Webb happened to catch MOME Z14 during an active burst phase, its extreme brightness becomes more understandable within the existing framework. This is the mainstream interpretation, but bursty star formation alone does not explain everything about MOME Z14. The brightness can be explained, the chemistry cannot. Because when scientists looked closely at the spectral data from this tiny, ancient, impossibly bright galaxy, they found something sitting inside it that had no business being there. Something that requires multiple generations of stellar life and death to produce. Something that takes billions of years to build. In a galaxy that was only 280 million years old, chemistry tells time. The elements inside a star or a galaxy carry a record of how many stellar generations came before them. Each generation of stars forges heavier elements in their cores and scatters them when they die. The more enriched a galaxy's chemistry, the more stellar generations have lived and died inside it. MOME Z14 has a problem. Its chemistry is too advanced for its age. The galaxy shows an elevated nitrogen to carbon ratio, higher than the Sun's, confirmed by spectroscopic analysis of its emission lines. In modern galaxies, this kind of nitrogen enrichment is associated with old stellar populations that have gone through multiple rounds of nuclear burning and stellar death, a process that takes billions of years under standard models. Here is why nitrogen specifically is the puzzle. Carbon is produced relatively early in stellar evolution. It appears in the cores of stars not much more massive than our Sun and gets scattered when those stars die. The first generation of massive stars, population 3, would have produced significant carbon fairly quickly. Nitrogen is harder to make in the quantities MOME Z14 shows. Producing elevated nitrogen to carbon ratios requires a specific class of stars called intermediate mass stars, roughly 1 to 8 times the mass of our Sun, to go through a particular phase of nuclear burning called hot bottom burning. These stars live much longer than massive stars. They take hundreds of millions to billions of years to reach that burning phase. At 280 million years after the Big Bang, there should not have been enough time for enough intermediate mass stars to complete their evolution and enrich the galaxy's gas to the levels MOME Z14 shows. Current stellar evolution models do not provide a standard explanation for this. Confirmed unknown. Several ideas are being explored. One is that the first stars were not just more massive than expected, but also had internal structures that produced nitrogen more efficiently than current models account for. Another is that very dense stellar environments, like the cores of early galaxies, where stars formed much closer together than in modern galaxies, could have accelerated certain nuclear burning processes. A third idea points somewhere unexpected: ancient star clusters in our own galaxy. Because MOME Z14's chemical fingerprint matches something astronomers have seen before, not in a distant galaxy, right here, orbiting the Milky Way. And that connection is one of the most striking things Webb has uncovered in the early universe. The Milky Way is surrounded by ancient, dense balls of stars called globular clusters. There are about 150 of them, orbiting our galaxy in slow ellipses that take hundreds of millions of years to complete. The oldest of these clusters are among the most ancient structures in the observable universe, formed over 13 billion years ago. Globular clusters have always been a puzzle. Their stars show unusual chemical patterns, including elevated nitrogen to carbon ratios that differ from the surrounding galaxy. Where did they form? Under what conditions? Astronomers have debated this for decades. MOME Z14 may have just answered the question. When spectroscopists compared MOME Z14's chemical composition to the oldest globular clusters in the Milky Way, they found a striking match. The nitrogen to carbon ratio, the overall pattern of elemental abundances, the compactness of the galaxy itself, all of them align with the environment thought to produce globular cluster chemistry. Confirmed observational match. The implication is straightforward but remarkable. MOME Z14 may be a direct ancestor, not a metaphorical one, of the globular clusters orbiting our galaxy right now. A galaxy that existed 280 million years after the Big Bang, forming stars in an incredibly dense, chemically active environment, may have eventually merged into a larger galaxy, contributed its stars to that galaxy's halo, and left those stars orbiting as globular clusters for the next 13 billion years. If that connection is real, it means the globular clusters you can observe through a backyard telescope tonight contain stars that were born inside an object, like MOME Z14. Stars forged in the earliest burst of star formation the universe ever produced, still burning, still orbiting. 13.5 billion years later, MOME Z14 also belongs to a broader class of compact, nitrogen-rich objects appearing in Webb data called little red dots. These are small, bright, chemically unusual galaxies appearing in surprising numbers in the early universe. They share properties with MOME Z14 and with each other, suggesting a common formation pathway. Whether that pathway involves extreme star formation, active black holes, or conditions unique to the early universe is still being determined. What is increasingly clear is that compact size and unusual nitrogen enrichment go together in the early universe. Small, dense galaxies appear to be the environments where nitrogen production ran ahead of schedule. Why that is the case is not yet understood, but these individual chemical mysteries inside MOME Z14 and its cousins are only part of a larger, more disorienting problem that Webb created. Because it was not just finding one or two unusual galaxies, it was finding them by the hundreds, and that number shook the foundations of the models built to explain the universe. Before Webb launched, cosmologists ran their best computer simulations of the early universe. They modeled how dark matter halos formed, how gas fell into them, how stars ignited, how galaxies grew. They predicted what Webb would find at different redshifts, how many galaxies, how bright, how massive, how spread across the sky. The predictions were careful. They were based on decades of observations and the most sophisticated physics available. They were also badly wrong. Webb pointed at small patches of sky and found bright galaxies in the first few 100 million years after the Big Bang, at roughly 100 times the rate the models predicted. 100 times. Confirmed by multiple independent teams analyzing Webb data, this is not a measurement error or a calibration issue. It has held up across different fields of view, different redshift ranges, and different analysis methods. This overabundance has a name in the astronomical community: the too bright, too early problem. Early galaxies are producing far more ultraviolet light than their estimated masses should allow, and they are doing it far earlier than galaxy formation models predicted. The problem has cascading effects. If early galaxies are producing so many more ionizing photons than expected, then reionization should have proceeded faster and started earlier than the old models described. But the Lyman alpha forest data, and the cosmic microwave background both point to a reionization timeline that does not fully match the extreme picture Webb's galaxy counts suggest. The different datasets are in tension with each other. Some researchers have formalized this as the photon budget crisis. We will get there in the next chapter. The more immediate question is, how do you explain 100 times more bright early galaxies than predicted? 3 broad categories of explanation have been proposed. The first is that early star formation was simply more efficient than the models assumed. Gas in the early universe may have converted into stars at a higher fraction than today, producing more light per unit of mass. The second is that dust played a smaller role at early times. In the modern universe, dust absorbs a significant fraction of a galaxy's ultraviolet output and re-emits it as infrared, making the galaxy appear dimmer in UV. If early galaxies had less dust, their UV output would be higher than mass alone would predict. The third, and currently most supported explanation, is bursty star formation. Early galaxies were not forming stars steadily. They were exploding into brief, intense bursts of stellar birth, during which their UV output spiked far above the average level. None of these explanations requires throwing out the standard cosmological model, but some researchers are not so sure the model survives intact. Think of a modern galaxy forming stars the way a factory runs production: steady, continuous, predictable, input raw material, output stars, maintain a consistent rate over billions of years. That is roughly how the models treated early galaxies before Webb. Now imagine the same factory, but with no reliable supply chain. Raw material arrives in unpredictable floods. When a massive delivery comes in, the factory goes into overdrive, producing at 10 times its normal rate. Then the supply cuts off, production crashes, then another flood arrives. That is bursty star formation. And in the early universe, it may have been the rule rather than the exception. Here is why: it produces galaxies that look impossibly bright. A galaxy's overall brightness in ultraviolet light is driven primarily by its most massive stars. Massive stars are hot and brilliant, but short-lived, burning out in just a few million years. During a burst phase, a galaxy forms enormous numbers of massive stars simultaneously. For a few million years, those stars flood the galaxy with ultraviolet light, making it appear far brighter than its total mass would suggest. Then they die. The UV output collapses. The galaxy dims. If you happen to observe that galaxy during the burst, it would look like a massive, luminous object. If you observed it during the quiet phase, it would look faint and unimpressive. The models that predicted what Webb would find assumed a steady formation rate, averaged over long time spans. Reality, apparently, was spikier. Northwestern University astrophysicist Claude-André Faucher-Giguère put it clearly: the brightness of a galaxy is more directly related to how many stars it has formed in the last few million years than to the total mass of the galaxy as a whole. A galaxy caught mid-burst looks like a giant. The same galaxy caught in a quiet phase looks like a dwarf. Webb may be systematically catching galaxies at their brightest moments. This theory fits the data reasonably well for many of the early galaxies Webb has found. It is consistent with the standard cosmological model. It does not require rewriting fundamental physics. But it comes with a prediction. If early galaxies are bursty, Webb should also be finding many faint, quiet phase galaxies alongside the bright one. The survey completeness at those extreme distances makes this difficult to confirm right now. The test is ongoing. There are also cases where bursty star formation alone seems insufficient. MOME, Z14's chemistry does not follow from burst activity. JADES, GS, Z131, LA's ionized bubble requires sustained radiation over a long period, which is harder to reconcile with an on-off burst pattern. Individual extreme cases keep requiring additional explanations beyond the general theory. Bursty star formation is the best available answer for the overall population. For specific objects, the mystery deepens, and the conflict between what Webb sees and what other datasets say is not going away. The universe has rules. One of them is conservation of energy. Another is that cause must precede effect. A third, relevant here, is that the number of photons available to ionize hydrogen must be enough to actually ionize it. Reionization required a specific budget of ionizing photons spread across the entire universe over hundreds of millions of years. Pre-Webb models calculated that budget based on the number and brightness of early galaxies. The calculation worked out. The photons produced by the galaxies scientists knew about were roughly sufficient to ionize the intergalactic medium by about 1 billion years after the Big Bang. Everything balanced. Webb broke the balance. By finding roughly 100 times more bright early galaxies than predicted, Webb effectively multiplied the photon budget. If all those galaxies were producing ionizing photons at the rates their brightness suggests, the universe had far more than enough photons to complete reionization much earlier. Models now suggest reionization should have finished somewhere between 550 and 650 million years after the Big Bang under the Webb galaxy counts, rather than the previously estimated 1 billion years. Confirmed theoretical revision. But here is where the contradiction enters. Two independent datasets place limits on how early reionization could have completed. The first is the Lyman alpha forest. When astronomers study quasars at different distances, the absorption patterns in their spectra reveal how much neutral hydrogen was still present along the line of sight at different cosmic ages. Those patterns suggest significant amounts of neutral hydrogen still existed until about 700 million years after the Big Bang, which is inconsistent with a very early completion of reionization. The second is the cosmic microwave background. The CMB contains information about when the universe became ionized, encoded in the way its photons scattered off free electrons during reionization. The CMB data constrains the total optical depth of reionization, which limits how early and how quickly the process could have occurred. An extremely early reionization completion is in tension with the CMB signal, so three datasets are in conflict. Webb says there were more than enough photons to ionize the universe early. The Lyman alpha forest says significant neutral hydrogen persisted until later. The CMB draws its own constraints. All three cannot be fully correct simultaneously under the current models. The possible resolutions are uncomfortable. Maybe some of the early galaxies Webb sees were not producing ionizing photons as efficiently as their brightness implies. Maybe large fractions of their photons were absorbed by dense clumps of gas inside the galaxies themselves and never escaped into the intergalactic medium. Maybe the Lyman alpha forest measurements carry systematic errors at high redshift. Maybe the CMB optical depth has been slightly misinterpreted. Or maybe something in the theoretical framework is genuinely off. The photon budget crisis is not solved. It is one of the central open questions in cosmology right now. And for some researchers, it points towards something even more unsettling about the foundations of the whole model. The standard model of cosmology is called lambda CDM. Lambda refers to dark energy, the force driving the accelerating expansion of the universe. CDM stands for cold dark matter, the invisible substance making up most of the universe's mass. Together, these two components, alongside ordinary matter, form the framework that has successfully explained almost every cosmological observation for 3 decades. Almost every observation, until Webb. The question now dividing the astronomy community is whether lambda CDM needs small corrections or fundamental revision. The mainstream position, held by most cosmologists, is that the framework is sound. The too bright, too early problem reflects incomplete astrophysics, not broken cosmology. The models predicted what galaxies should look like given assumptions about star formation efficiency, dust content, and feedback processes. Those assumptions were wrong in detail. Correcting them within the lambda CDM framework by allowing for burstier star formation, lower dust content, and higher gas-to-star conversion efficiency can bring the predictions much closer to what Webb observes. Under this view, no new physics is required. A smaller but vocal group argues otherwise. Researchers at Case Western Reserve University and elsewhere have pointed out that JWST's observations align surprisingly well with predictions made by modified Newtonian dynamics, or MOND. MOND is an alternative theory of gravity that modifies Newton's laws at very low accelerations and eliminates the need for dark matter. Under MOND, structure formation in the early universe proceeds faster than lambda CDM predicts, naturally producing more massive and brighter early galaxies. This is a minority position. The vast majority of cosmologists find lambda CDM more compelling overall and consider the astrophysical explanation more probable. MOND has its own unresolved problems and does not explain all observations as well as lambda CDM does across the full range of cosmic scales. But the debate is real, and it matters because the stakes are high. If lambda CDM survives Webb intact, with only astrophysical corrections needed, then our fundamental picture of dark matter, dark energy, and cosmic evolution is essentially correct, just lacking in detail. If it does not survive, if some new gravitational physics or early universe mechanism is required, then the entire framework built over 30 years needs rebuilding. The evidence so far leans towards survival with corrections. Bursty star formation, reduced dust, higher star formation efficiency. These adjustments are plausible and do not require abandoning the model. Each new Webb discovery tightens the constraints further and gives theorists more data to work with. But a model that requires patching everywhere it touches the early universe is a model that deserves scrutiny, and Webb has not stopped finding things that need explaining. Before Webb, the assumption was that the heavyweights ended the Dark Ages, massive, luminous galaxies blazing with ultraviolet radiation, punching large ionized bubbles through the neutral fog, driving reionization across cosmic distances. The big players doing the big work. Webb changed that picture. In 2025, using Webb data, a team of astronomers identified 83 tiny starburst galaxies, all actively forming stars, when the universe was about 800 million years old. These were not impressive objects individually. Small, faint by the standards of spectacular galaxies like JWST, Z13, LA. But they were forming stars at intense rates relative to their sizes, and they existed in far larger numbers than anyone had accounted for. When researchers added up the total ionizing radiation from all 83 galaxies combined, the number was substantial. Despite each one being individually underwhelming, together they matched or exceeded the total ionizing output of the rare, luminous giants, confirmed by photometric and spectroscopic analysis. This points toward a fundamentally different picture of reionization. The fog was not primarily cleared by a small number of blazing beacons. It was cleared by an enormous population of small, faint, ordinary galaxies working collectively, each one carving a tiny bubble, each bubble eventually merging with its neighbors. Think of it this way. One lighthouse in a harbor provides a bright, obvious beacon, but a harbor lit by 1,000 small candles spread across every surface provides more total light, reaching into corners the lighthouse cannot. The universe apparently lit itself up the second way. This has a practical implication for how scientists search for the engines of reionization. Focusing only on the brightest, most spectacular early galaxies misses most of the action. The real drivers may be below Webb's current detection threshold, galaxies so faint that even Webb struggles to confirm them individually, but whose collective contribution dominates the photon budget. It also suggests that reionization was not a smooth, uniform process. It was patchy. Some regions cleared early because they happened to contain dense concentrations of small galaxies. Other regions stayed neutral longer because galaxies were more sparse there. The fog lifted unevenly, region by region, bubble by bubble, over hundreds of millions of years. The large, spectacular objects like JWST, Z13, LA, and MOME, Z14, were the first lights in the darkest rooms. But the dwarfs were the ones that opened all the windows. and Webb has barely begun to count them. MOME Z14 sits at redshift 14.44, 280 million years after the Big Bang. It is the farthest confirmed object in human history. But is it close to a limit? Or is there still deeper territory Webb can reach? The honest answer is that we do not know exactly where Webb's ceiling is. But physics sets a hard wall that no telescope ever built can break through. That wall is the cosmic microwave background. At 380,000 years after the Big Bang, the universe was opaque. Light could not travel freely. Everything before that moment is forever hidden behind a curtain of scattering photons. No optical or infrared telescope can see through it. The CMB is the ultimate horizon. Between that wall and MOME, Z14 lies about 100 million years of cosmic history, still unexplored by direct observation. The first stars ignited somewhere in that gap, the very first galaxies assembled inside it. Webb may be able to push into that territory. Theoretical estimates suggest Webb could potentially detect a galaxy or a star-forming region at redshift 20 or higher, corresponding to roughly 180 million years after the Big Bang, under the right conditions. It would need to be an unusually bright object, a concentrated burst of star formation, or a luminous active black hole, and it would need to fall within a field Webb is already targeting with long exposures. The probability of finding such an object is uncertain. The universe at that epoch may have had fewer luminous sources. The neutral hydrogen fog was thicker, potentially blocking more signals. Detection would require both luck and careful survey design. There is also an instrument consideration. The most extreme redshifts push emission lines into mid-infrared wavelengths that fall at the edge of Webb's sensitivity range. Webb's MIRI instrument covers mid-infrared wavelengths, but with lower spatial resolution and sensitivity than NIRCam and NIRSpec. Detections become harder. Webb's successor is already being discussed. The next generation of space telescopes, including concepts under early planning, would push further in both sensitivity and wavelength coverage. But those instruments are decades away from launch. At best, for now, Webb is the instrument, and within its capabilities, it is still finding new record holders. The team that discovered MOME, Z14, has identified additional candidates at even higher redshifts that require follow-up confirmation. Each one has the potential to become the new most distant object ever seen. The race to the beginning has not ended, it is just getting harder. And what we find in that final gap between MOME, Z14, and the CMB horizon may answer the most fundamental questions still open. When exactly did the first star ignite? When did the very first galaxy form? How close to absolute darkness did the universe actually come? Quasars are among the most powerful objects in the universe. Supermassive black holes actively consuming enormous amounts of matter, releasing energy equivalent to trillions of suns from a region smaller than our solar system. They can be seen from almost any distance, and that visibility makes them one of the most powerful tools in cosmology. When a quasar's light travels toward us across billions of light years, it passes through clouds of intergalactic gas along the route. Wherever it encounters neutral hydrogen, specific wavelengths of that light get absorbed. Each cloud of neutral hydrogen leaves a dark notch in the quasar's spectrum. Because the universe is expanding, each cloud of hydrogen along the line of sight is at a different distance and therefore at a different redshift. That means each cloud absorbs the same wavelength of light at a slightly different point in the quasar's spectrum. The result is not one absorption line, but dozens or hundreds of them, stacked up across the spectrum like the teeth of a forest. Scientists call it the Lyman alpha forest. By reading the forest, astronomers can map the distribution of neutral hydrogen across cosmic distances and time. A spectrum crowded with absorption lines means a line of sight passing through lots of neutral gas. A clear spectrum means the gas along that path is mostly ionized. For studying reionization, the Lyman alpha forest is invaluable. By examining quasar spectra from different distances, scientists can track when and where neutral hydrogen was still abundant. The point at which quasar spectra transition from thick, saturated absorption to a clearer signal corresponds roughly to the end of reionization in that region of the universe. Before Webb, Lyman alpha forest analyses consistently placed the end of reionization at around 700 million to 1 billion years after the Big Bang. The spectrum became clear by that point. That seemed to match theoretical expectations. Now Webb is creating tension with those measurements. If Webb's galaxy counts imply a photon budget sufficient to ionize the universe much earlier, but the Lyman alpha forest says significant neutral hydrogen was still around until 700 million years. Something is inconsistent. The most likely resolution is that the escape fraction of ionizing photons from early galaxies was lower than assumed. Photons produced inside the galaxy get absorbed by dense gas and dust within the galaxy itself before they can escape into the intergalactic medium. If only a small fraction of a galaxy's ionizing output actually escapes into the surrounding fog, the effective photon budget is much smaller than the galaxy's total brightness implies. This is a testable prediction. Webb is now being used to directly measure escape fractions in early galaxies, attempting to determine what fraction of their ionizing photons actually make it out. The Lyman alpha forest will not be overturned by a single discovery, but its tension with Webb's galaxy counts is exactly the kind of productive conflict that drives science forward. The old timeline had a comfortable structure. The universe was born in the Big Bang. It went dark. Darkness lasted a few 100 million years. Stars and galaxies formed. Over the following 600 to 700 million years, they slowly ionized the surrounding hydrogen. By 1 billion years after the Big Bang, the job was done and the universe was transparent. Webb has cracked that timeline open. JWST 131 LA shows that reionization had already begun, locally at least, by 330 million years after the Big Bang. That pushes the confirmed onset back by at least 270 million years compared to prior estimates. Confirmed, MOM Z14 exists at 280 million years after the Big Bang, well within what was considered the heart of the Dark Ages, and it is so bright that it must have been contributing ionizing photons to its surrounding environment even earlier. The galaxy counts showing 100 times more bright early galaxies than predicted imply a photon source that was far more powerful and far more active in the first few 100 million years than anyone anticipated. If the revised picture holds, the universe did not slowly warm up like a car on a cold morning. It ignited in scattered places early and ferociously, then those burning regions spread and merged. Some corners of the universe may have been fully ionized by 400 million years after the Big Bang, while others remained largely neutral for hundreds of millions of years longer. Reionization was patchy, uneven, driven by galaxies clustered in some regions and absent in others. The fog did not lift uniformly. It cleared in patches, leaving neutral islands that persisted long after their surroundings had gone transparent. This new picture aligns with a growing body of theoretical work that predicts exactly this kind of patchy reionization. But it required Webb's discoveries to turn the theory into something observationally supported. The practical consequences for cosmology are significant. Models of large-scale structure formation depend on the timing and pattern of reionization. The heat deposited into the intergalactic medium during reionization affected how gas clumped afterward, which affected how galaxies formed in subsequent billions of years. If reionization was earlier and patchier than assumed, those downstream effects need to be recalculated. The entire cosmic history timeline is being adjusted, not torn up, adjusted, with more precision, more detail, and more accuracy than was possible before Webb flew. And adjustments this significant always point toward a question at the end. What does it ultimately mean for where everything came from? By about 1 billion years after the Big Bang, reionization was complete. The neutral hydrogen fog that had covered the universe for hundreds of millions of years was gone. The intergalactic medium was fully ionized. The universe was transparent in the way it remains today. What followed was a period of rapid growth and transformation. The first galaxies that had been small and fierce during the Dark Ages began merging. Smaller galaxies fell into larger ones. Their gas pools combined, triggering new rounds of star formation. Supermassive black holes that had been growing during the reionization era continued to feed, reaching masses billions of times that of our Sun, becoming the quasars that lit up the young universe with extraordinary power. Dark matter halos grew as well, their gravitational wells deepening, pulling in more and more gas from the cosmic web of filaments connecting everything. The filaments themselves became more pronounced, the voids between them emptied further, and the large-scale structure of the universe, the cosmic web, solidified into the pattern we can map today. Over the next few billion years, galaxies took on familiar shapes: spirals, ellipticals, irregulars. Star formation rates across the universe peaked about 3 billion years after the Big Bang, a period astronomers call cosmic noon, when galaxies were forming stars at rates hundreds of times higher than the modern universe. That peak slowly declined as gas supplies were consumed and black hole feedback drove gas out of galaxies. The Milky Way assembled during this period through mergers and accretion. Stars like our Sun formed in the second half of cosmic history from gas enriched by 10 billion years of prior stellar generations. The heavy elements in your body, the carbon in your cells, the iron in your blood, the oxygen you breathe, were all forged in stars that lived and died before the Sun existed. The globular clusters orbiting the Milky Way today formed in environments that may have looked like MOME Z14. The ionized bubbles carved by galaxies like JWST, GS, Z131, LA were the first cracks in the fog that eventually cleared into the transparent universe. Those clusters have been orbiting through for 13 billion years. The Dark Ages were not just a prologue, they were the foundation. Everything that exists now grew from the structure built in that period of total darkness. From the gravity-shaped ripples in neutral hydrogen, from the first fires that ignited in collapsing clouds. The universe we live in is the result of the Dark Ages ending, not just beginning. And the most striking discovery of all is still ahead. MOME Z14 existed 280 million years after the Big Bang. Its light has been traveling for 13.5 billion years. It is the most distant confirmed object in human history, and it may be one of the great-grandparents of the Milky Way. Let that sit for a moment. The chemical fingerprint inside MOME Z14, that elevated nitrogen to carbon ratio, that unusual pattern of elemental abundances, matches the oldest globular clusters orbiting our galaxy right now. These clusters formed over 13 billion years ago. Their stars are the most ancient we can observe directly, burning in slow, red-tinged stability, relics of conditions that no longer exist anywhere in the modern universe. If the connection holds, MOME Z14 did not just exist in isolation at the edge of the observable universe. It eventually merged with other galaxies. Its stars became part of a growing structure. Over billions of years, through mergers and tidal stripping, those original stars from MOME Z14 ended up in the halo of whatever galaxy absorbed their original home. And that galaxy was, eventually, part of the chain of mergers that built the Milky Way. The stars in globular cluster Omega Centauri, the largest globular cluster orbiting our galaxy and visible from the southern hemisphere without a telescope, may contain stellar descendants of stars that first ignited inside something like MOME Z14. Stars born in the first 300 million years of the universe, still burning 13.5 billion years later, close enough that you could see them tonight if you are in the right hemisphere. This is what makes the Webb discoveries not just distant and abstract but personal. The atoms in your body followed a chain that started in the Big Bang, passed through population 3 stars in the Dark Ages, was scattered by supernovae, collected into second-generation galaxies, enriched through further stellar death, incorporated into the molecular cloud that became our solar system, and assembled into you over 4.5 billion years. MOME Z14. is not something separate from human existence. It is a chapter in the same story, the same matter, the same processes, the same physics, operating across different scales of time and space. Webb has not just found the farthest galaxy, it has found a piece of the chain that connects the darkness before stars to the world you are standing in right now. The universe began in total darkness. It ignited in one spot, then another, then millions. The fog cleared, galaxies grew, stars lived and died and gave their elements to the next generation. And after 13.8 billion years of that process, here we are, pointing a golden mirrored telescope at the darkness and reading the beginning of our own story. We are not separate from the cosmos. We are what the cosmos did with 13.8 billion years of darkness and fire.